Well, thank you. A wonderful introduction. So today's talk is about nebulae. And nebula is Latin for clouds. So we're talking about clouds in space and some of the ones that we can see. Now, partly it's a reason to show you some of the most beautiful pictures. It's always, nobody minds observing them again, as taken through some of the biggest ground-based and space-based telescopes. But it's not just a case of looking at pretty pictures and thinking, oh, wow, aren't they spectacular? I'm also going to try and decode what you're seeing. What I want you to be able to do is to read the picture and, literally be able to see what the science is behind the beautiful pictures, what it is you're observing, and why astronomers use these images, why we take these images with these telescopes. It's not just because they're pretty, what we're learning from them, and what we're learning about the constituents of space. So when you look at a galaxy, any galaxy, whether it's our own or the other external ones, the key thing that you see are the stars. They delineate all the structures in the galaxy. And in particular, when you have a spiral galaxy, you see the blue stars that form the spiral arms. And blue stars are young stars. They're hot stars. They're massive stars. These are stars that don't actually live very long. They have lives of only a few tens of millions of years. So if you see blue stars, they're relatively recently formed, and they line the spiral arms of our galaxy and other galaxies out there. So when you look at this galaxy, you can see the spiral arms and these knots of star clusters, and these are called open clusters. And here's just examples that you can see through binoculars very easily at the minute, the double star cluster in Perseus, where you've got about 300 stars in each cluster. Now, this is an example of one of those open clusters within our galaxy, kind of the next spiral arm over. And that's why it's so easy to see. And when you've got a cluster of stars like this, they all formed around the same time from one big cloud of gas and dust. But today's talk, even though it involves star formation, and you will see these star clusters in all the pictures I show you, because they're a key ingredient of what I'm talking about, today I'm going to talk about the space between the stars, the interstellar medium. And that's not a complete vacuum, as one might suspect. It's still a much better vacuum than you can ever get in the lab on Earth. So we do call it a vacuum, but it's not completely empty. So, for example, if I scooped up a volume of space, say, about the size of this water bottle, maybe I'd have a few dozen hydrogen atoms in it. If I was lucky, I might have a little grain of dust, and I'll tell you what dust is in a bit. But it's not completely empty. There is matter between the stars. And a lot of it is primordial. It's left over from the formation of the galaxy, so it's hydrogen and helium. There's also a lot that has been recycled through stars. And all of this is really vitally important for our understanding of the whole galaxies and the stars, because all this matter between the stars is a reservoir. It's the material that stars form from. Okay? And understanding the interstellar medium and the places and the environments where it forms the stars, and not just the stars, but the planets around the stars, and if you really want, the life forms that live on the planets around those stars, we all come from the matter I'm talking about today. And so an understanding of that gives an idea to the process how planets like Earth, stars like the Sun, and species like us came about. Now, when you look between the stars, obviously, this is a schematic. You have hot stars, you have young stars, and you've got gas filling this space, and all kinds of different gas. There's a very hot gas, very diffuse gas, that you could only see if you have X-ray eyes, if you could look through an X-ray telescope. That's not what I'm talking about today. That's at temperatures of thousands of degrees. There isn't a lot of mass in it. It's very dispersed. But embedded within this, there is much colder gas. There is clouds of neutral hydrogen atoms. Now, again, these are cold gas clouds, and these are only visible with radio telescopes. So like the radio dishes you get along the Barton Road if you come to Cambridge, the big radio dishes pick up this very cold gas. And it's this cold gas that eventually goes on and forms stars. And it sits in the plane of our galaxy, that disk, that flat disk of the galaxy, and it even extends further out from stars. There's a colossal amount of invisible gas there. So that's there, and within this there are denser clumps, patches where that is more, it's denser, it's more clumpy, it's colder. And as far as we're concerned, and today's talk is mainly about visible nebulae, the kind of ones you might go and observe with your own telescope if you're lucky enough to have one. Where they become visible and relevant to optical astronomers is when they're very close to those bright blue stars. Blue stars put out a lot of energetic photons. They excite the gas atoms. Just like Andy was talking about with the oxygen in the atmosphere. If you excite an oxygen atom, it'll store that energy for a while and then re-release it as the green light that you see in the aurorae. It's the same in space. You excite an atom and later it releases the light as a nebulae. And that's where it becomes visible. And that creates a lot of the spectacular things we can see in the sky. So you have the stars. And these nebulae are apparent when you look at an external galaxy. Again, here's a nice one that's kind of face on to us. And you can see the star clusters along the spiral arms. But alongside them, you've got these little glowing pink patches. Those are the nebulae I'm talking about today. And if I go to a nearby example in our own galaxy, here you have the Rosette Nebula. Classic case. Now, the first thing you'll notice is a star cluster sitting right at the center, a small group of bright blue young stars. And these stars are about 4.5 million years old, and that's young in astronomical terms. Now, they formed all at the same time from one cloud of gas. And they formed where it was densest at the center. Little pockets collapsed down and formed those stars. And now they've switched on. They're producing lots of light, lots of energetic ultraviolet light. Not just that, there are also winds of charged particles, again, like Andy mentioned, from the aurorae that stream from the sun. There are even stronger winds from young stars like these that blow out. So first of all, those energetic photons light up the gas from the gas cloud in the immediate vicinity. Because when a cloud collapses down and forms stars, it's not an efficient process. You don't use all the gas in the cloud before the stars switch on. There's a lot left over. And in fact, there'll be a cloud that extends way out of this picture, most of it invisible, cold gas. We're just seeing the stuff that's closest to the stars where it's being excited. And it's radiating predominantly in pink, because hydrogen is the most common element in these gas clouds. And if you heat hydrogen atoms, the strongest light they give off is this pinky red color. So you'll see that many of these nebulae are pink, even though there are other atoms that contribute to the colors, like oxygen, neon, sulfur, nitrogen, that we also observe. So that's the first thing you notice. The nebulae surrounds a star cluster at its core. And you can also see the star cluster has excavated a cavity around it. It sits in a little bubble. And that's because not only is the energetic photons going out and exciting the gas, but the physical winds from the star are pushing back on the gas. They're heating the immediate environments of them. We know hot gas expands, so the bubble around them grows. And then you've got the winds that push back. And they just clear a little space around them, and then you have this structure. And just to give you an idea of scale, this thing is about 100 light years across. Okay? So these aren't diddy little systems. These are big structures. And this is probably about 5,000 light years away from us. So we have stars, and we have gas, both cold gas and then the gas that's caused to glow because you've warmed it up to a few thousand degrees. There's another ingredient, a very vital ingredient, especially for planet formation, and that is dust. Now, we call it dust, and we don't mean dust in the sense of dark matter that you might get in the Philip Pullman books, for example, if you read those. Dust are solid particles, and they're solid particles that are tiny. They're about 1/10 of a micron across, and if you want to put that into a scale, it's about 1,000th of a human hair across. So they're tiny particles of silicate and carbonate, so literally, soot and sand. And that may not sound, very impressive tiny particles, but if you have clouds of them embedded in the gas that are light years long, there's so much matter there, it can obscure any light from the background source. So here's another galaxy, again face on. You can see the star clusters along the spiral arms. You can see the nebulae, but you can also see dark patches that line the spiral arms here. Those are not absence of stars. Those are dark because there's a screen in front that's blocking out the light of the stars. And you can't separate out the gas from the dust. The dust is embedded in the gas clouds. The denser the gas, the more dust there is packed within it. So for example, again, going to, well, you can see here this dust, it lies in the plane of the galaxy with those spiral arms. Now, here you're seeing a galaxy face on. When you see one of these spiral galaxies edge on, the dust is concentrated in that disk. And it's so opaque, it's almost like it's splitting the galaxy in two. Now, remember, for our own galaxy, we live in the disk about halfway from the center to the edge. And when we look into our galaxy, this is our perspective. As we look into our galaxy, we are looking along that plane. So when you look at the Milky Way in the night sky, and you see it as a band, you are looking just at this side view of our galaxy. And then if you look towards the center of the galaxy, you will also see that within that band of stars, you have dark features, which are the dust in our galaxy, just like in this one. So if I fade into a view of our galaxy to show you the perspective. Okay, I bet it never gets this good from Colchester. It certainly doesn't from Cambridge. I have cheated a bit. This is a picture from New Zealand. And the wonderful thing about the southern hemisphere is you're looking right into the core of the galaxy. So the Milky Way looks so much more fantastic. But here immediately you can see that you've got the bulge in the center of the galaxy here. This is the disk. And all these dark structures, these dark nebulae that you can see with your unaided eye in the night sky in the southern hemisphere are due to dust clouds. So here, for example, there's a very famous one known as the Coalsack. Again, it's visible with the unaided eye, as are all these diffuse structures. There's another one just here called the Pipe. Okay? And these are just those diffuse clouds of dust blocking out the background light. And altogether, the dust and the gas are mixed together. And so the dust are an important part of the nebulae. They're part of the matter that the stars and the planets that come from these gas clouds have formed from. So here's a picture of a nebula. Now, you've got to imagine, it's almost like something like this. It's almost like you're peeking into a cave, right? You've got a little pocket of stars that have created a hole around them, and it's just broken out, so you're allowed a privileged view into the center of what is a mostly invisible cloud. And the stars are here, and you can see they're surrounded by a cavity, and the gas is glowing pink around them. And then you've got these dark, obscuring blotches that are the dust clouds. Now, if I zoom in with progressively more powerful telescopes, so these are the young stars, and then zooming in with the Hubble Space Telescope, here you have drifts of denser cloud pockets embedded, with dust embedded in them. And you can see sometimes the dust is so thick that these clouds are completely opaque. They block out the light from the background stars. And not only do they block out the light from the background stars, they're blocking out the heat. So this means for a cloud like this, the denser regions, and these are some of the densest regions of the interstellar medium, not only is the starlight not getting through the cloud, the heat from the stars not getting into the core of the cloud. So right in the center of the cloud, it's very cold. Its temperatures of a few tens up to perhaps 100 degrees above absolute zero. It's the kind of environment when all those chemicals in space join up and form molecules, not just water, oxygen, carbon monoxide, hydrogen atoms, carbon dioxide. You get really exotic chemicals. You get formaldehyde, ammonia, methane, ethane. There's very complex chemistry within these clouds. They're known as molecular clouds. And again, you can only observe them in infrared and millimeter, submillimeter and radio wave bands because they are so cold. But be aware that there's very complex chemistry going on in outer space. And it's predominantly carbon-based, if that's of interest. There are silicon-based molecules, but there's a lot of organic compounds within these clouds. So these are cold, and they're very dense, and they contain the dust particles as well. One very famous nebulae, of course, is in the Sword of Orion. You'll be able to see that with the unaided eye, maybe even from Colchester, either early mornings at the minute or a few months on. But the whole region of Orion is a region where there is masses of dust and gas in space. If we just take a deep picture that picks up all the pink light from the going gas clouds and some of the dust in this region, you will see it's all embedded in dust and gas. And if we zoom into this region, you have the very famous Orion Nebula. But just down here, alongside Orion's belt, you have another very famous nebula. And if I zoom in on that and turn it round, there we have the Horsehead Nebula. Or as some kids I spoke to recently called it the Loch Ness Monster Nebula, which I think we should promote that. It's a good name. And immediately you'll see there's an edge of a cloud here. You've got the pink gas that's actually it's evaporating away, it's getting heated up, it's getting excited, it's giving off that pink light. And this star is probably responsible for heating that. But what I hope you see is there are many more stars up here than there are down here. Okay, so you know there's something blocking the light from some of the background stars. Now, if we zoom in around the Horsehead and look at a Hubble Space Telescope picture of just this Horsehead, there are three things I want you to note. The first one is there's a very sharp edge here, and you can see some of the gas evaporating away, perhaps. There's a sharp edge because the winds from the stars are eating into the cloud. There's physical erosion taking place. The second thing I want you to note is there's a young star just breaking free of the dust and gas cloud there. That's your first indication, observationally, that these regions are associated with star formation. The coldest, the densest regions within these clouds are the ones that produce the stars and the planetary systems around them. And then the third thing I want you to note is I want you to compare the colour of the stars that you see outside the cloud to the ones you see through the cloud. And this is the bane of astronomers. Dust is there. It's endemic through our galaxy. And it has effects on starlight. You can't always tell where the dust is. But nonetheless, it makes starlight redder. Okay, if you see a star normally and a star through the dust cloud, the one seen through the dust cloud looks significantly redder. It's lost its blue light. And this is a process known as scattering. It's an interaction between the light from the star and the particles of dust within the gas cloud. And it's analogous, well, okay, here's an example, not to scale, by the way. Here's the Earth, and here's a very distant star. It's giving off blue light. It's giving off red light. Now, imagine there's a gas cloud with lots of dust in between us and that star. What happens is the light that's coming towards us travels through that dust cloud. But there are physical collisions between the blue photons and the dust particles and the red photons and the dust particles. And the way this process of scattering works is a particle will very efficiently scatter light that's got a wavelength less than its size. What this means effectively for the kind of size of the dust particles we see in space, they scatter the blue light, but not the red. So there are physical collisions, and the blue light, which would have travelled towards you, gets scattered every which way, and you're only left with the red light that makes it to Earth. So it looks like the star's been reddened because you've lost the blue light. So on Earth, you'll observe this at sunset and sunrise, and that's not due to dust, though sometimes that accentuates this effect. It's due to just particles, molecules within our atmosphere. When you see the sun again, not to size, okay, not to scale, but when you see the sun at midday, you're looking through less of an atmosphere depth than when you see it at sunset or sunrise. You're seeing through more of the atmosphere and more through the denser part of the atmosphere. So you get more scattering of the blue light, and you only get the red light remaining. And so things seen through dust, through thick columns, get reddened. And it's not always obvious it's there. Here, for example, are two side-by-side nebulae in the sky. One, however, is a lot more distant than the other, and I can know that immediately from looking at this picture because you see they're not the same red. It is the same process, it's the light that's being given off, but this one is more distant because all the light from the nebulae has been more significantly reddened because it's gone through a longer depth of space to get to us. And a neat thing about this dust scattering, I mean, okay, it's a pain, it changes how we see things, but it also makes these dust clouds visible when they might not otherwise be. So I've told you about the scattering that goes on in our atmosphere. Okay, it's just in case you've forgotten what a blue sky looks like, right? We get blue, our air is invisible. The only reason we see a blue sky is that we're seeing all this blue light that's been scattered. So if I'm down here and I'm looking directly at the sun, I see all the colours of the sun coming towards me, unless, of course, it's down at sunrise. But when I look up at the sky, I'm seeing all the blue light that's been scattered by all the other sunbeams coming in at other parts of the sky. So in the same way that the scattered blue light renders the whole atmosphere visible, when you look in space, sometimes dust scattering will make different kinds of nebulae. So I'm not sure if you can quite see this, but there's a star field and a dark dust cloud here that's blocking out the light from the background stars. Now, when it gets close to this particular star, that star's not really bright enough or energetic enough to make the gas glow pink. However, there is dust cloud around it, and what you're seeing is that scattered blue light. So this is, light from the star that would have gone perpendicular to our point of view, and it's scattered off the dust clouds, and it creates what's known as a reflection nebula. And so you get this very blue component, which is the scattered light. It's not the ionized gas. And you'll see this on a lot of the nebulae as well. Just because it's Halloween, I have to put this one in. This is Rigel. Here you have a lot of dust cloud, and there's this particular dust cloud. It's called the Witch's Head Nebula. Hope you can see there's her hat and her nose and a nice witchy chin. Yeah. And that nebula appears blue, not just because the light from Rigel in Orion is very blue, but it's scattered light. And so it's that very characteristic blue colour. And there are other ways we can see the dust. Here you have faint pink glow from the gas clouds. Here you can see obscuration. There are more stars up here than down here. That tells you you're looking at the edge of a dust cloud. Now, remember I said that it blocks the heat and the light from the stars. That energy's got to go somewhere. And what it does is it warms up the dust grains just a bit. It warms them up to temperatures of a few tens up to perhaps a couple of 100 degrees above absolute zero. And things at that temperature, like each and every one of you in the audience, glow in the infrared. So we know the dust cloud is there not just because it blocks the light and scatters the light, but because it also glows. So I'm going to move to the same picture now in the infrared, and you see how the light from the dust in the clouds becomes immediately apparent. And so by looking in infrared light, you can see the pattern of this dust throughout the sky. And this is one of the reasons, there's another one coming up in a minute, why a lot of modern telescopes use the infrared. It's one of the reasons the James Webb, the next space telescope will operate in the infrared. It's not just to see the most redshifted galaxies, it's also to be able to see the distribution of dust and the coldest regions in our galaxy. And there's another aspect about observing in the infrared, which is that you can see into the clouds, and it's all to do with scattering. Again, imagine you've got a little star cluster embedded deep within one of these dusty clouds. It sends off blue light, it sends off red light. They even give off infrared light. Now, if you've got a really opaque dust cloud, you've got a lot of dust and gas between you and the star cluster, the blue light will get scattered. Even longer wavelength red light gets scattered, and only the infrared light makes its way out of the cloud. And so remembering that, I'll go back to this picture. Look around here, and around here, and you will see that there are star clusters that become apparent, that are hidden from view, but the light, the infrared light from them, breaks free and can make it through the dust. And so this is the other reason we use infrared, so we can see right into the dust clouds to where the star formation is taking place. Here, just for another example, I showed you the horse head. I'll show you a picture in the infrared where the clouds become invisible, or you can, the stuff that's opaque suddenly starts to glow, and you can see those these things that are reddened, you can see them as they truly are within the cloud. It no longer really looks like a horse head or a Loch Ness monster. You can play this game with galaxies. I can't resist this. I've told you that you've got these veins of dust that line the spiral arms. This is a visible image. Let's just go to the infrared. It's almost like you turn the galaxy inside out. The stars are too hot to give off much infrared. What really glows are the dust lanes within the galaxy. Do you want to see that again? There we go. And so the dust is glowing. So we've got our ingredients now. We've got stars, we've got the dust lanes, we've got the gas clouds, and they all coexist within these nebulae. And just to say, actually, where the dust comes from, It's formed within the atmospheres of old, like red supergiant stars. Here, for example, this is an infrared image. I like the arrow. That's the star, right? This is VY Canis Majoris. That is just about the biggest known star we know about. It's about 30 to 40 times the mass of the sun. It's kind of just flexing its muscles before it goes supernova. It's giving off. It's so distended that the outer layers aren't held on very well. They tend to kind of be billowing off. And you can see it's surrounded by a big cloud of matter that's coming off from the outer envelope. Now, this is just a spectrum. If you don't like spectrum, just ignore it. But reads, you've got various molecules. You've got lots of water. You've got carbon monoxide. These are being formed within that cloud of stuff that's coming off the star. But all of this infrared light is due to dust. This is glowing because there's dust. And so you've got this very cool outer envelope of these giant stars. It's exactly the right place conditions to create these dust particles. And so if you've got a lot of dust, it means you've had a lot of star formation in the past. So if we put this together, here's a classic nebula. This is the Eagle Nebula. It's called that for reasons which are totally not apparent from this image. If you have a wider picture, you've kind of got an eagle's head, and these are its wings. And again, think of it as looking into a cavity, into a cave. You've got a star cluster here, and you've got the bubble it's created, and the walls of the cave are being lit up, being illuminated, the gas is glowing, and then you've got the darker structures around the edge, which are the opaque dust clouds. Now, within this nebulae, there are lots of structures, and I want you to note that a lot of these opaque structures are pillars. And this is true in all the pictures I show you. Now, there's one down here, and this is the Hubble Space Telescope picture of it. And that's 9.5 light years long. And you can see at the top, there's gas being lit up, but it also looks as if it's moving. There's stuff being pushed off and being, not only is the gas boiling off, but it looks like some of the dust is being blown off and blown away. And what you're seeing here is a process of erosion. It's not just the light, but also the physical winds from the star erode the surrounding structures in the gas cloud surrounding them, but in this very particular way to form pillars. And it's almost like you've got a dense blob here, which acts as an umbrella. So just to explain, okay, there's just the top. You can see stuff lit up, boiling off, and then being pulled off. Imagine you've got a big cloud of gas, the walls of that gas and dust cloud, and some regions are denser and thicker with dust than others. So the blacker it is, the more dust, the thicker your gas cloud, and this is the light, fluffy stuff. And then somewhere above the ceiling, I turn on some young stars. You've got the winds from the stars, you've got the radiation from the stars. They eat into the gas cloud. But as they eat in, they erode the fluffy stuff more quickly. And what you find is those more opaque, thicker blobs act as a protective layer. And gradually, you build up naturally this column of protected stuff behind it. So you have the erosion at the top, and the stuff behind it doesn't see the winds or the light. And so you build up these pillar structures that always point, you can see here, all around the edge of the cloud, towards the star cluster. They're here in this one, which was my opening picture. You can see them in the Rosette Nebula, which is a much younger system, pointing in towards the center. And back in the Eagle Nebula, don't just have this one. If I zoom in on these three, this is your iconic Hubble Space Telescope poster. The pillars of creation, they call them. And all you're seeing is erosive processes taking place. Not only do you get these long columns, but you can see everywhere there are outcrops. They've also been eroded. And all these fingers point towards the stars that are doing the erosion. And here again, I hope you can see material boiling off. And so you get structures. It's not just that the stars, all of this is in symbiosis. Here you're seeing that the stars are formed from this gas cloud, but then the effects of the stars are then eroding and creating the structures that we observe around them. And, there's a lot more that if I had another half hour, I'd tell you about how they promote star formation going on. Because, of course, you've got this process of stars collapse from these clouds, But the dust, you know, as these stars, they don't live very long, they go supernova. When they explode, they redistribute that dust, they distribute those heavy elements that they forge at their cores back into the surrounding clouds, and also that shockwave can compress the gas and maybe generate another generation of star formation further out in the clouds. And so you've got a whole process that is dynamically active and going on all the time. And so all these dust clouds, dust that you see forming these pillars, has been formed in previous generations of stars within this system. We're just seeing a snapshot of the evolution of this whole nebulae, which over the timescale of the universe has been changing immensely in all this time. Now, one final aspect of these I want to show you that is only apparent really if you've got a Hubble Space Telescope at your disposal. But it's just reinforcing the idea that it's these dark, cold patches that are the best places for gravity to do its work. I mean, if you're going to form a star, you've got to pull stuff together under gravity. If stuff is hot, it's moving around, and it's kind of moving around too fast to notice the gravity of all the surrounding particles, and it doesn't collapse very easily. These cold, dense pockets where stuff is closest together, it's relatively still, it notices the gravity and star formation takes place. So if I zoom in at the top left pillar here at the top, you can see that stuff is being eroded off, it's boiling off, and there are little clumps that are being left behind. Those that, I think I just ring them so you can see some of them there. Those are the cocoons of matter that will go on and form individual stars and form the next burst of star formation. Now, sometimes the light, fluffy stuff gets eroded around them and they get left behind, and then they go on and form the new star cluster. And you know, they're in a cocoon, and the material that doesn't go into the star will then perhaps settle down and form a planetary system. But this also goes on deep within the cloud, but this is the area that's invisible to us unless you go into the infrared. I mean, we have hints already that there are the star clusters within the clouds from the infrared, but if we go, for example, to the Carolin Nebula, down in the southern hemisphere, absolutely fantastic, wonderful object for an amateur telescope. You just need to be in the right hemisphere. And with the Hubble Space Telescope, they've zoomed in on this region to create a fabulous mosaic. It goes way on beyond what I can squash onto this picture. And you've got all these features. You've got the pillars. You've got the young star clusters. You've got places like here. You've got those dense molecular clouds. I love this one. It's called the caterpillar. And this one's also a personal favourite. So you didn't think the universe was doing a rude hand gesture to us, did you? But, you know, these are all regions where the next generation of star formation will be going on. A lot of the light, fluffy stuff has been eroded around, leaving those dense pockets that will be coldest and densest, full of molecules, and form the next generation of stars. And in some of these pillars, it's already happening. Over here, there is a region that if I just zoom in on that, and a slightly more technicolor version from a later Hubble Space Telescope observation, and I'll just whiz it around. You can see within the pillars here, there are kind of jets coming out. And that is a key clue. There's a very young stellar object. It's not even old enough to be known as a star. But just as stars get their act together, you know, how much stuff they have to radiate and how much to not blow themselves apart, there's a kind of exhaust jets that come out for a few hundred thousand years, just from a very young star. And you can see them coming from deep within these pillars. Again, suggestions that within those pillars, star formation is taking place. The last, one of these pillars within this nebula is the last feature I want to show you here. This is a visible image. The pillar, stuff eroding off. You can see a few red stars within the core. You can perhaps see there's a kind of wisp of stuff over here, and a wisp of stuff over here, maybe even a bow shock. If you go to the infrared, you can see it's a young stellar object deep within that pillar that's producing these jets. And you begin to track what's happening within these pillars. So I hope I've given you a glimpse of the kind of structures we see in these nebulae, what they mean and why they're of interest to astronomers. But just to flag, there are, of course, thousands of fantastic pictures that I couldn't possibly fit into a half-hour talk. And you may well be already aware of these websites, but just in case there are any relative beginners to them in the audience, 3 websites where you can go and browse many more pictures of nebulae. The first one is Astronomy Picture of the Day. Put that into your favourite search engine. Every day there's a NEAS space picture. It could be about space science, it could be about the aurorae that Andy was talking about, it could be about nebulae, it could be about planets, with a little text of explanation. Every astronomer worth their salt, it's the first website you check every day. And a lot of these pictures are available on there. If you like the visible images, go to the Hubble Heritage Gallery, where they're all available to download, use as your favourite wallpaper, again with an explanatory text, so you can then have a go at what I've told you and try and decode some of these nebulae yourself. And if you're interested in the infrared images, there's a lot from Herschel and Vista and Planck that you can look at, but the best gallery of infrared pictures is probably built up from the Spitzer Space Telescope, which works in the infrared. But hopefully I've given you a taste, and you can go on and start exploring for yourself some of the science behind the beautiful nebulae. Thank you.